Hi, everyone. My name is Kaarthik. I work at Microsoft, and I'm excited to be here to talk about the near real-time data pipeline we have implemented for processing Bing events using Spark Streaming API. So some of the problems we are going to look at today are probably relevant only at the scale of this data pipeline. So I wanted to set the context on the scale that we are talking about for this data pipeline. So Bing is Microsoft's search engine. It powers Bing.com and other internal and external partner services like Cortana, MSN, Yahoo Search, Apple Siri Search, etc. So billions of requests are sent to Bing every month. And Bing is enabled by hundreds of services in the Bing stack. And these services run across tens of thousands of machines on various data centers across the globe. And these services, excuse me, these services generate huge volume of logs. Specifically, this particular pipeline processes about 13 terabytes per hour. And the processing requirements for dealing with these events vary by scenarios. And as you can imagine, there are lots of scenarios to process these events and get value out of them. And there is no one single framework that satisfies all the requirements. So there are lots and lots of frameworks involved to process this data. And for this particular, the pipeline that we are going to look at today, it's based on Spark. And we are going to look at the different issues we had in using Spark at scale, and the solutions that we went with to proceed and then complete the pipeline. So these services that power the Bing stack produce a lot of events, as I mentioned. If you look at the events in isolation, they offer very little value. So it's important to have a collective view of all the events across all the services and kind of connect them by the request. So one request comes to Bing, lots of services get used, and each of these services produce a log, and the curated data set that kind of connects all these events to every single request is very valuable, because the collective view contributes directly to the monetization of the service, as well as improving the service, whether it's about the relevance or whether it's about the other qualities like availability, improving latency, so on and so forth. Traditionally, this curated data set was created using batch processing. It was easier to do. It was easier to process static data. So data would arrive at one place, and then processing would happen, and this curated data set would be created for downstream consumers. And as the business grew, it no longer made sense to wait for all the events to arrive at one place. Several people have asked me what kind of system we have in place, or we had in place to process, to do the batch processing. So we have this system called Cosmos, and it's an internal system. Incarnation of this system is available in Microsoft Cloud Azure as a part of Azure Data Lake offering. But this original implementation of Cosmos, it's similar to Hadoop, if you will. It had a storage layer with a distributed file system similar to HDFS, and it had an execution engine called Dryad, which is a general purpose, more expressive engine than MapReduce, and query language called Scope, which is a higher level scripting language for declarative programming. So life was all good. Data would arrive in Cosmos storage, and then folks would write Scope scripts to process the data and produce this curated data set. As the demands grew, we wanted to do it on time. We could not wait for hours to get the insights from these events. So the processing had to be done as the data arrived, as opposed to kind of collecting data in one place. And the pipelines evolved into near real-time pipelines from batch processing, and that introduced lots of issues. For example, the obvious problem is the data is generated so fast, and the first problem is to deal with the volume, the incoming volume. And because we were dealing with events as they arrive, we had to deal with issues like out-of-order arrival, right? There is no sequence in which the events can be expected. And if you think about the events generated by services across the globe from different data centers, lots and lots of layers are involved. And to process, we have to collect the data. And there is no guarantee on the ordering. And in fact, there is no guarantee on the latency for these events to arrive in this processing pipeline. Even though it's near real time, we want to see these events arrive in these pipelines as soon as possible. But because of the distributed nature, things will not be as smooth. Events get delayed, events get lost. So it was important to manage some kind of state to deal with these issues. And managing state is very expensive, and it's very hard to get it right. So let's see how we used Spark and build this pipeline to address some of these issues. So let's look at the high-level overview of this pipeline. So this pipeline is called the event merge pipeline. So what happens is when a request comes to a data center, to Bing, lots of events are generated. And in this context, the context of this pipeline, let's look at 3 different events: a gateway event, the UI event, and then a click event. So these events need to be collected and then merged. And these events are pushed to the Kafka, local to the data center, to the corresponding topics. And there are several data centers that do the same thing. The next step is to process this using a streaming pipeline. And this implementation, as I said, there are several implementations of this pipeline exists, but we wanted to try out Spark. And so this pipeline, this talk is about the Spark implementation. And this whole pipeline is implemented in C#. So Mobius you see there. So that is, it's an open source project that enables C# language binding to Spark. The reason that is important to us is because, as I said, traditionally, the data was processed in Cosmos infrastructure, and that supports C#. So all the libraries were implemented using C#. When we wanted to try out Spark, there was no way to do that. And it was not practical to re-implement everything that was needed in the languages supported in Spark, Scala, Python, or Java. So it was not practical to re-implement that or fork the code base. So the only way we could reuse the existing years of investment is by having C# language binding to Spark, and that's what Mobius is about. So as we were building Mobius, we also implemented this pipeline. And like I said, the whole implementation is in C#. So the issues we are going to look at are not specific to the C# binding. So even if we had implemented this in Scala, we would have had the exact same problems because, like I said, these issues are caused by the scale of the data being processed and not necessarily the language implementation of this pipeline within Spark. So the first step in the pipeline is reading the data. So all these events need to be read from all data centers, all topics. And the next step is merge the events. So one request generates these events. So we need to tie events generated to the original request so that we can do all the analytics downstream. The events get lost. The events don't arrive on time. So it was important to maintain this 10-minute window to wait for the late arriving events. And this 10-minute window is defined by the business requirement. The business says that, business requirement states that if an event arrives after 10 minutes, it's okay to kind of consider that lost and not do anything with it. So the 10-minute window is a very important requirement for us. And if you think about the size, it's just humongous, right? Because that's the state I'm talking about. Managing that size of the state is very hard and very expensive. I'm not going to get into details on that because that's a separate talk in itself. So after merging, the merged events are sent to Kafka, a different Kafka topic. From there, all the downstream consumers consume and then do their analytics. And like I said, the curated data set is created in this pipeline, and that curated data set is available in Kafka, the destination Kafka in this picture. Now let's look at different problems we had in this setup. So the first one is unbalanced partitions. So the data in partitions of all these topics are not evenly distributed. And as a team that owned this pipeline, we had little control over the configuration of Kafka and then how data gets pushed to Kafka. So we had to just take it and then make it work. So unbalanced, we had to deal with the unbalanced partitions. The second issue is slow Kafka brokers. Occasionally, Kafka brokers would get slow, or they would appear to be slow from the pipeline point of view. So we had to deal with that. Otherwise, it would cause delay in the pipeline, and beyond certain point, the pipeline would never catch up. So it is important for us to make sure that the delay did not accumulate in the pipeline as the batches get processed in the pipeline. The third thing that I want to talk about is the read step. To read data from Kafka, we had to get the offsets, the range of offsets to read data from. And that turned out to be very expensive. I'll talk about why. And lastly, I wanted to talk about join logic. So we had to implement this join logic, hand-code it, because there is no feature available in Spark to do that based on the application time. It's straightforward doing that, but just that we had to hand-code that join logic. So all of these, the issues that I'm talking about is based on Spark 1.6 version that we used. So some of them may not be relevant or applicable to Spark 2.0. We have not updated the pipeline yet, but and then Spark 2.0 at some point will have the application time support. Now let's look at these problems in detail. The unbalanced Kafka partitions. So we used Direct API to read data from Kafka, and that maps like one single partition in Kafka to RDD, this one-to-one mapping. And if the data is not evenly distributed in Kafka, it will not be evenly distributed in Spark RDDs. So what happened is that the largest partition in Kafka became the long pole in processing in Spark. And we noticed that like most of the tasks would just complete fast, and then like one or two partitions would take forever to finish. And that obviously increased the batch time. We didn't want that, right? We want each batch in processing to complete as soon as possible. So one option is to call the repartition method in these streams. The problem with that is that it had to shuffle the data, and that can be expensive depending on how the data is distributed across partitions. In our case, it was very expensive because there is one partition that had a big fraction of data for each batch, and then the repartition wasn't practical. So what we did is we had to implement this thing called dynamic partition Kafka RDD. It's just an override of, we extended the existing Kafka RDD implementation, and then introduced this threshold, which will help create multiple RDDs for each Kafka partition. So in that sense, we could guarantee a distribution. Like if there is a huge partition, we broke that down into multiple chunks so that these chunks can be operated in parallel in Spark. So So this particular solution worked for us because it did not matter for us whether this one single partition in Kafka is processed as one partition in Spark or not. But in some cases, it may not work, especially like if you have a hard dependency on how the partition is laid out in Kafka. So this approach, you have to kind of think carefully before employing this approach. So that's the first problem, unbalanced Kafka partition. It was relatively straightforward to solve that problem. So the next thing is slow Kafka brokers. Kafka brokers can get slow for some time or extended periods of time. And like I said, even if we let the Kafka brokers stay slow for like 30 minutes, in our case, the pipeline would never catch up. It would always fall behind, and the outputs will always be delayed. And this delay accumulates. So we did not want that to happen. Even 30 minutes is like, it's very important. So what we did is, if you think about a batch, it has the first step, which is read, and second step is process. By making this asynchronous, we made sure that the read or the fetch data always started on time, right? Every batch, in our case, it was like 2-minute intervals. So the fetch job would always start on time. And the processing would just pick up from what was fetched, and then the processing would happen. So all we had to do is have a separate thread that did the fetching, data fetching from Kafka, and then processing would follow, depending on the time it would take to process. And here again, like this approach worked because the processing is much longer than the actual read time. So it turned out that we could make things fit together within that batch window, and it worked, it helped. The third problem that I mentioned is kind of related to the previous one, but this is specifically about the cost in getting the offsets. So to read data from Kafka, we need to do the offsets, and reading has to loop through all the combinations. So we have several data centers, and we have 3 topics, and each topic has an average of about 170 partitions. So just looping through that to read the data before processing for that particular batch turned out to be very expensive. So in this case, we noticed that our batch window was 2 minutes. Right? Everything has to happen within the 2-minute window, read and process, and then it should be ready for the next batch. But our initial experimentations showed that just to kind of get the metadata and then the offset, it took about 10 minutes for that window. So it turned out to be very expensive because it was kind of sequential. So what we did is we moved this getting the offset to a separate thread. And we not only got the offset in the thread, but also we materialized the data from Kafka so that when the processing starts, the data is already there in the cluster. We don't have to kind of go and read it as a part of this processing phase. So read and process, right? So read would not just read the offsets, but also materialize. And again, like this happens in parallel. And by the time processing is about to start, the data is already materialized. So, so that's how we dealt with this expensive find offset step in the whole pipeline. And the last thing that I mentioned in the pipeline is join. So we had to handcraft this join. So Spark has update state by key API. So all we had to do is we had to leverage that API, but we had to plug in our own handcrafted join method. And this join method enforced this window, the 10-minute window that he talked about. So at a high level, what this method did is it kept track of the watermark. So as the events arrive, it kept track of the maximum time. Think of that as the watermark. And the window, the 10-minute window, is defined by that watermark. So as the watermark moved, that the kind of window moved. So there was talk yesterday about joining 2 Kafka streams. I think they talked about following a similar approach. having update state by key as a main implementation, but having a customized join function that took care of joining the two different Kafka streams. And that was yesterday's talk. And we had to do that for 3 different Kafka streams. So yeah, so the state is maintained here, and that state had to be checkpointed, and checkpointing was very expensive, so we had to invent some approaches to make that fit within our time window, because the whole thing, right? Read, process, checkpoint, everything has to kind of finish on time for the application to stay in sync with the events as they arrive. Otherwise, it would fall behind and never catch up. So, so those are the issues that I wanted to talk today. I think we are open for questions.
First, thanks a lot for the talk. My question is about the 10 minutes window. You say that you want to join all the events that are related, and they are related only if they are in the same window of 10 minutes. But when you get an event at the end of the window after 9 minutes and a half, how does it work? Because you will not get the 10 minutes window for the events after, because they will be get on the next step.
Right. So that's why if you go with the default, how Spark works, right? It kind of uses the batches and then tries to join. We cannot rely on that, because one event for a request, for example, the gateway event may arrive first in the first batch, but then the corresponding click event may arrive as a third batch or whatever, right? So 2-minute window, 2-minute window, 2-minute window, right? The first 2-minute window, you have the gateway event, and then the third 2-minute window, you get the click event. And these need to be joined, right? So that's why this 10-minute window is really important. If you just go with how Spark works, it will just look at 2 batches, right? So you have one batch that has the gateway event, or like the time window, sorry, I shouldn't say batch. So within the time window, so you have the gateway events arrive, a group of gateway events, and then a group of click events. And it may not match. Most likely it won't. So that's why this 10-minute window ensures that even if this click event arrives in the third batch, you can still join and produce the output. So that's why that window is important. So Spark Streaming, when you do the join, when you call like dstream join, it just goes with the batch, what is available in the batch from 2 different streams. And that is not enough when you think about real-world scenarios. It's very important to have something more than that. Yeah, because you cannot, there is no application time that is supported, right? Like the only thing that is supported is Spark's own notion of time. So Spark has this notion of time, and the 2 different D streams have the same, share that time. And that has nothing to do with the application time or the event time. That's why we had to invent our own join method, or use the own join method to enforce our own application logic of joining, as opposed to Spark's notion of joining 2 different streams.
So how do you manage the deployment of your streaming application? And the second question is, how do you monitor do you have like your custom monitoring around your Spark jobs? Because Spark monitoring, in my opinion, is rather primitive.
Yes, so deployment, like I said, we had some issues with checkpointing, and that directly is related to deployment. So we had to kind of invent or try, we had to try out different things, and we had to customize how checkpoint worked. So yeah, there is no good answer to that. We tried out different things, and deployment is not smooth, especially because of the checkpoints. We try to minimize. So this logic, right, doesn't change much. So thankfully, we don't have a versioning problem, right? You go from one version to the next. the whole checkpoint becomes useless. We don't have that problem. But still, as we were developing, we had to deal with some of the issues related to checkpoint. But the main issue we had was on the time it took to checkpoint that massive state. It's 10-minute window, right? I talked about the 13 terabytes per hour. So if you think about 10-minute window, it's huge, right? It's a good fraction of the 13 terabytes, and that has to be checkpointed. So that was the main problem we had. And as far as monitoring, you're right. We are not happy with the existing level of monitoring, especially for the scale. So it's something that we are trying to see how we can improve. Either build something or try to leverage what is out there in the community. But we have not narrowed down on anything yet. So far, the focus has been to just to get it to work and deal with all the scale problems. Then monitoring is obviously once things work, the next step is monitoring and then how to make it better. Unfortunately, we don't have a good answer to that. Sure.
How do you integration test your system? Do you test your system by running some shadow stack before deploying that to make sure that things work?
Yes. So there are different levels of validation that happens. The first step is dev box testing, right? So we have this application, and we have the sample data on which this thing is run. But obviously, it is not enough. There are lots of issues that happen only in production or real setup, especially with the configuration and all those things. So even though we have different layers of testing, there is nothing that is real until it gets to the final stage. But you can validate the logic, for example, using the local or DevBox testing. So that validation we do in DevBox, but the real thing happens only because there's configuration involved, and this configuration there are for example one of the things I mentioned is having a threshold for the topics, right, for the dynamic repartitioning, and that is per data center per topic, and along with other Spark configurations. So there has a lot of things to configure, and things will eventually go wrong. So those things, there is no easy way to catch that with prior testing. So the first step is to validate the logic. DevBox testing is good, but then something happens as a part of deployment and then monitoring what the output. And that is the real validation that tells us that everything is working.
Hey, have you had any stability issues with, especially keeping the jobs long running and processing the data? And did you do any configuration changes related to this?
So we had some stability issues, occasionally tasks would just fail and executors would crash. So we had those kind of things. But nothing that was consistent that we had to do something beyond what is already available, right, in Spark. But definitely, those issues happened, but most of those issues were transient in nature. So it wasn't worth investigating, figure out what happened in that 2-minute window, because it's just transient, and then there were bigger issues to deal with. But yeah, things, there were some stability issues, but like I said, it's mostly transient in nature.
I noticed in one of your earlier slides, you had the Kafka on the remote data centers. Did you use Mirror Maker at all to get that data to a Kafka cluster on the Spark server, or is it a direct connection?
It's just direct connection. Yeah, we
Direct.
didn't have any mirroring or anything.
Did you look into using Mirror Maker at all? Or?
So there is a team that manages Kafka, and then they have some requirements for mirroring and all those things. But it's mostly transparent for us. And all we did is use the direct API to connect to Kafka and then read it, even though it's remote. And that's why the slow Kafka brokers issue was important. Because sometimes when we go across the globe to read it from Kafka, it was slow. And the batch cannot wait for us to kind of, read from like some data center in Asia and then, deal with the latency. So yes, that's why, we had to work around that issue, but we did not have to directly deal with mirroring or read from a mirror that is closer to us.
And that's all the time we have for questions. Thank you.
Thank you.